Hello. In this video, we will be going over the idea of U-substitution. Then in the next couple videos will be examples. So the idea of U-substitution when it comes to integrals is that we want to turn an integral into something that we know the antiderivative of, something that we can easily integrate even if the integral originally was something more complicated. And what U-substitution goes along with in the idea of antiderivatives and derivatives being opposites is U-substitution goes along with the chain rule. So the chain rule said that if I'm taking the derivative of a composite function, so a function where I have one function nested inside of another, then the derivative of that function will be the derivative of the outside with the inside plugged in place, then times the derivative of the inside function. What U-substitution strives to undo is take this derivative and go backwards and figure out what was the original function that we would have taken the derivative to get there. So what U-substitution says, the substitution rule, says that let U equal g of x. Let U be an inside function where the derivative of g is continuous on an interval and let f be continuous on the corresponding range of g. All this setup sentence is saying is let these two functions work together with continuity and differentiability so that we can make the following composition. Then on the interval where the composition can work, the integral of f of g of x times g prime of x dx is equal to the integral of f of u du, which this f of u should now be a simpler function. No, and now it is now in one variable, not this function going on inside. Now, practically speaking, what is the steps we need to go through for U-substitution? Practically speaking, we will look at these examples in the next video. I'm going to put our steps over on the side. First step is that given an indefinite integral involving a composite function f of g of x. We want to identify an inner function g of x so that a constant multiple of the derivative of g appears in the integrand. Once we identify that function, and again, we're looking for a function where we also see its derivative. Once we identify that function, we're going to take that function and call it u. And we're going to take the derivative of that function. We're going to substitute all that out inside our integrand, or inside the integral. Step 3 is now, when we make the substitution of u and du, our whole integral becomes in terms of u. So we now have this new integral in terms of u that we can evaluate. And finally, step 4 is we have evaluated the integral, but our antiderivative is in terms of u. We are trying to find the antiderivative of something in terms of x. So we need to put it back in terms of x, which is just taking all those u's and putting g of x back in. So write the result in terms of x using our substitution, u equals g of x. So there is our procedure for indefinite integrals, meaning integrals without bounds, when we're just trying to find the antiderivative. We can also use U-substitution on definite integrals, meaning integrals with bounds. Again, these are the examples we will see in the future next videos. But the procedure for U-substitution with definite integrals changes just a little bit. So our procedure is with definite integrals, given a definite integral, involving a composite function, f of g of x, we want to identify the inside function. So same first step. We want that inner function to be such that a constant multiple of g prime of x, so a constant multiple of the derivative, appears in the integrand. So we see both the function and its integral, and its we see both the function and its derivative. Grand. There we go. Step 2 is to, just like before, substitute u equals g of x and the derivative du equals g prime of x dx in the integral and turn the whole integral into being in terms of u. But we need to turn the whole integral in terms of u. With this substitution, all we've done is change the differential on the end from a dx to a du and change the variable using our function g of x into a variable of u. On a definite integral, we also have these bounds. And these bounds are in terms of x. They're saying along the x-axis, from 0 to 1, from 0 to square root pi over 2, from 1/3 to 1. Along the x-axis, I am finding the area under this curve. But when this differential changes into a du, we're now in a whole different realm. We're no longer talking about the x-axis. We're now talking about something that's been shifted into essentially a u-axis. So we need to change those bounds as well. So step 3 is a little bit different. That we need to change the bounds of the lower bound and the upper bound to be in terms of u by plugging it into our substitution. We have, these are in x, and we've made, with our substitution, a way u and x relate to each other. So we take the thing in terms of x and plug it into our substitution, and we'll turn it into being terms of u. Now our whole integral is in terms of u, including the bounds, meaning now we have something to evaluate and get a number. So we can evaluate the new integral. And since at the end of this, we would get a number, there's no switching back to x that needs to happen. The integral with respect to u and the integral with respect to x give us the same value with this substitution. So once we evaluate the integral in terms of u, we're done. That is the integral evaluated with respect to x. So for definite integrals, once we switch over to being in terms of u, we can stay in u. But for indefinite integrals, since we don't have those bounds, we need to make sure we go back to terms of x at the end. We will see examples in the next 2 videos about these different procedures.